Alrighty, y'all. Today we're taking a look at part 2 of our Physics 211 homework number 2. A lot of 2s. So we're doing the infamous cat in the elevator problem today. So we're going to jump right into it so that this video isn't 3 hours long. Right? So we have our cat Mary, who can jump 120 centimeters off the ground, which I can immediately just change 1.2 meters. Right? And we need to find with what velocity must Mary leave the ground in order for her to jump 120 centimeters high. And we also want to note that that velocity is a property of Mary, and no matter what situation she's in, that initial velocity is the same. Right? So we have to figure out with what velocity must Mary leave the ground in order to jump my 1.2 meters high. So if I'm phrasing this like one of our solvable sentences, then I'm going to ask myself, what is the value of v naught? What is the value of my initial velocity, right? The velocity that Mary leaves the ground with. And I'm asking, what is the value of v naught so that she can jump 120 centimeters, right? And now I want to know, how do I know that it's the correct v naught that I'm getting there? That's my second half of the sentence. How do I know that the v naught that I just solved for is the one that gets her to 120 centimeters? Well, if I'm jumping with greater than that v naught, right, if this is her y as a function of time, right, so say this is the perfect jump that gets her to the 1.2 meters, right, if she jumps with greater than that initial velocity, she'll overshoot and she'll intersect that 1.2 meters, but she'll intersect on the way up, and then she'll also hit that height on the way down again. So we're going to assume that she's not actually jumping more than my 1.2 meters, right? And I'm also going to assume that she actually reaches the 1.2 meters, because if my v naught was less or too small, then she wouldn't actually make it all the way up there. In order for my velocity to be the correct velocity, it has to be the velocity at which she gets to 1.2 meters at the apex of her jump. Right? So what is the value of v naught so that she reaches 1.2 meters at the apex, or y of t is 1.2 meters, I should say, at the time when, you can just see my handwriting slowly getting worse, at the time when, and now I have to say, okay, at the time when she's at the apex. Well, how do I know that she's at the apex? Well, in that case, before the apex, I'm going upwards, and after the apex, I'm going downwards. So somewhere in between, I have to switch from my positive velocity before to a negative velocity after. So somewhere in between, I have to cross 0. And that's going to be my apex, because that's the sign that I'm no longer going up, and I'm about to start going down. So at my apex, v of t equals 0. And because this is just, she's just jumping up and down, this is a one-dimensional problem. That's why I'm not using any subscripts. I can use subscripts. I can say that my y velocity will be 0. And that will be the case when I'm at the apex of a 2D problem. My y velocity will be 0, but my x velocity might not be. But in this case, since it's just a one-dimensional problem, I don't have to write all the subscripts because we're not specifying something in the x and something in the y. We're just thinking about the one dimension. So now I have this beautiful question posed. Now I have to actually figure out how to solve it. So we could start by saying, okay, the time when v of t equals 0. I find the time that my velocity is 0, and then I plug it back in to my position equation. But this is a 1D problem. I'm solving for time in velocity and plugging into position. We have our third kinematics equation that did that for us. Vf squared minus v naught squared equals 2a x final minus x initial. Right? And just to keep things consistent, I'm going to swap these for y. Right? This is our third kinematics equation. And in my problem, right, I know my v final. We just said my v final is when my velocity equals 0. We're solving for v initial. Right, so I'm saying that I know this. I'm trying to solve for this. I know my acceleration because Mary in the air is in free fall. Right, so her acceleration will be negative g because I've been drawing up to be positive. I know my y final. That's going to be my 1.2 meters. Right, I want to get to 1.2 meters. And I know my y initial because I'm setting that at the ground. I'm setting that to be 0. Right, so if I do the same thing that I normally do and list out all my possible variables just to clearly specify what I'm setting each number to. All right, my v naught, v of t, my acceleration, and my time. All right, my y initial is 0. My y of t we said was 1.2 meters. My v naught, that's what we're solving for. My final velocity, or my velocity at the time that I care about, is going to be 0. I should probably specify meters per second in meters. And my acceleration will be negative g. Right? Because again, I said up was positive and gravity is down. I don't know my time and I don't need it just yet. Actually, the next question is going to ask how long she's in the air, so I'll have to solve for time, but we'll get to that for the next one. In the meantime, I can plug in some of my numbers. Well, my v final was 0. My y initial was 0. So making this look a little bit nicer, minus v naught squared equals 2 times minus g times yf. Right, so solving for v naught, I want to just drop the negative on both sides. So I'm just dividing by negative 1. V naught squared equals 2g y final. Again, I don't like plugging in my numbers just yet. I'll plug in g and I'll plug in zeros to make my equation look a little bit nicer. But I don't plug in my numbers until I have it solved all the way for v naught. In this case, I just took the square root of both sides of my equation. And now I plug in my numbers. My v naught will be the square root of 2 times 9.8 times 1.2. Right. And that will give me a number of around 4.85 meters per second. All right. I rounded up just slightly, but that is going to be Mary's initial velocity for the next 3 problems. Well, this one and then 2 more. All right. So now I have to figure out how long will she be in the air before she lands. So what is the value of, well, I'm solving for how long she's in the air, so I'm solving for time. What is the value of t when, I guess we could say at the time when, but we're solving for the time when. All right, what is the time when, I mean, how do I know that she's landing back on the ground? That'll be when my position equals 0. Right? So my last part of my problem, what I could have done is I could have said, I solve for my time. I say my velocity equals 0. I solve for the time when my velocity equals 0, and then I can plug that back in, right? That velocity, that time, that velocity equals 0 would have been dependent on v naught, right? Because that would have given me my expression in terms of v naught that I could then plug in. And then I could have used that expression for time to get the time to the apex. I just would have had to plug my v naught back into that. I could have get the time that it takes for Mary to get the apex. But I'm not asked the time that it takes to get to the apex. I'm being asked to solve for the time until she lands again. So in this one, I'm going to set up my y of t equals y naught plus v naught t plus 1/2 a t squared. And again, my y naught I set to 0, my y I set to 0, my v naught I just solved for, and my acceleration is still negative g. So plugging all that in, making it look nice, I have 0 will equal v naught t minus g over 2 t squared. So then I'm solving for t. So 0 equals t times v naught minus g over 2t. Right? And that tells me that t equals 0 is one of my solutions, which makes sense because my position equals 0 at time 0, because my y naught, which is my position at time 0, is 0. So it's that other factor that's the more interesting one. So I'm going to set that equal to 0. I'm going to add this to the other side of my equation. V naught equals g over 2t. Then I'm going to multiply both sides of my equation by 2. So I'll get 2v naught, I'll switch back to my normal color, 2v naught equals gt, and then I can divide both sides by g, which gives me that time equals 2v naught over g. Now I can plug in 2 times my 4.85 meters per second divided by my 9.8 meters per second squared. That will give me a time of roughly 0.9897 seconds to land back on the ground. Now the fun part is that I started and ended at 0, which means the path of Mary while she was in the air was uninterrupted, and it was this nice symmetrical parabola. So had I solved for time to apex, right? So that's my time to apex. My time to landing would have been twice my time to apex. Right? And that only works because Mary is following this nice clean parabola, right? And she starts at 0 and ends at 0. Right? So my time to apex is going to be equidistant to both of my intercepts. So since I start at 0, all of these math words to say that I double my time to apex to get my time to land. So had I solved for time first, I could have just used that expression. So maybe I made a little bit more work for myself by taking the easier equation in the first part, but it wasn't too bad. So we can just move right along to the cat in the elevator. Right? So now Mary is in an elevator, and the elevator is accelerating upwards at 2 meters per second squared. Mary jumps and tries to hit one of the elevator buttons, and the elevator button is 110 centimeters, or 1.1 meters above the floor of the elevator. If Mary jumps as high as she can, will she be able to push the button? Now, there's a few different ways we can approach this. First thing that I want to do is sketch a graph of what's going on in the problem. So I'm going to first draw Mary. Right? The same exact trajectory she was on before. She's just jumping. And if the elevator floor wasn't moving at all, she would come back to exactly where she started. But something else is happening. But her free fall flight is exactly the same as it was before, because also she has the same initial velocity that she had before. Right? Then I'm going to sketch my graph of the elevator button. So the elevator button starts 1.1 meters above where Mary starts. So if we say Mary starts at 0, the elevator button starts at 1.1. And the initial velocity of the elevator is 0. So it'll start kind of horizontal. It'll start with a horizontal tangent line, but it'll be accelerating upwards. So it'll look something like that. It'll be an upwards facing parabola. So if I want to figure out, will she be able to push the button? Well, based on my sketch, it looks like these two curves, these two graphs intersect, right? Now, I could be wrong, right? It could look, it could look something like this. It could actually intersect more this way. All I know is that it's coming out horizontally, and my graph isn't very well drawn to scale, right? So I want to find out, will she be able to push the button? That's just asking, is her position ever the same as the button's? Does she ever cross the path of the button? So if I could get my position as a function of time, I wrote that as x, we changed that. We're talking about it in terms of y, right? If I can get my position as a function of time for the cat, and my position as a function of time for the elevator button, then I just need to find the intersection. And if I can find an intersection, that means they intersect, right? So my position of the cat that's going to be, as a function of time, that's going to be y naught plus v naught t plus 1/2 a t squared. Right? And again, this is the exact same position versus time equation that I set up for the previous problem. So my initial position is 0. My initial velocity we had solved for in the previous problem. I'm just going to leave that as v naught for right now. And my acceleration is still negative g, so I'll do minus g over 2 t squared. And that's my position of the cat as a function of time. It's going to be a beautiful parabola. Now I just need the position of the button as a function of time. I'm going to set up the same thing. So yb of t will be y naught plus v naught t plus 1/2 a t squared. And we said that my initial position of the button, because Mary starts at 0, the button's going to start 1.1 meters above her. So I can say equals 1.1. We said the initial velocity of the button was 0, so I can get rid of that term. And the initial acceleration of the button was 2. So if I plug that in, I'll get plus 1/2 times 2 t squared. Right? And there's another difference is that I have a negative acceleration because my gravity on the cat is still down, but my positive acceleration because my elevator is accelerating upwards. Right? And 2 divided by 2, I can simplify that just a little bit more, just to make it nice to look at when we're solving later, plus t squared. So now if I want to find the time when their positions are the same, I'm going to take my equations and set them equal. So essentially I'm saying that yc of t equals yb of t. So I take my expression for yc of t, and I'm just going to copy it so I don't have to rewrite it. Move it down there. And I take my equation for yb of t, and I set them equal. Now all that's left to do is solve for t. So I'm going to go on this side of my equation, I'm going to subtract 1.1, and I'm also going to subtract t squared from both sides of my equation. So I'm also just going to rearrange it so my t squared term is out front, because that's how I like to look at quadratics. So it'll be minus g over 2 t squared minus t squared plus v naught t stays where it is, and I minus subtract 1.1, and that's all going to equal 0. So I'm just going to simplify this a little bit more. So this is the only time I'm going to probably plug in 9.8 for g ahead of time, because this is going to be negative 9.8 divided by 2, so it's going to be 4.9. So negative 4.9 minus 1, so it's negative 5.9 t squared plus, and again I'll plug in my 4.85 t minus 1.1 equals 0. Now this is of the form at squared plus bt plus c equals 0, which means I get to use my best friend, the quadratic equation, right? Which is negative b plus or minus the square root of b squared minus 4ac all over 2a. So my b was 4.85 plus or minus my square root of b squared minus 4 times a was negative 5.9, c was negative 1.1, all underneath my square root, and then I divide by 2 times a was minus 5.9. All right. Now, usually I say this is a job for a calculator, but we can look at this a little bit. Right? It's gross, it's all decimals and numbers, but what I'm going to get out eventually, if I'm just simplifying this inside bit, right, I have my negative 4.85 on the outside, plus or minus square root. I'm going to end up with 25.5225 minus 25.5225. 0.96. Now, and then 2 times A is negative 11.8. Right. Now, inside this bit here, we have a number subtracted by a larger number, which means this is going to be negative. And I can do the math if I wanted to. It's like going to be negative 0.4 something. But either way, this is going to be a negative number. I can't take the square root of a negative number. I'm not capable of doing that. I'm not a wizard. So what this then tells me is that there is no time where they intersect. Because remember, that's what we were solving for. We were solving for the time where the position of the cat is the same as the position of the button. And because this is undefined, all right, it's a square root of a negative, that tells me the cat never reaches the button. Which also means that my graph was a little inaccurate. Probably should have looked something a little bit more like this. And in fact, if I were to plot this on Desmos, it would look something a little bit more like this, where the cat doesn't quite reach the button in the elevator. Right? So, a long process for our first part of this question, but now we get to solve for how much time will Mary be in the air for if she jumps in the elevator. So, now, instead of thinking about if she intersects with the button's path, now we have to think of when she intersects with the floor. It's not a matter of if she intersects with the floor, it's when. Right? The floor starts at the same place as Mary, but it's going to follow the same kind of trajectory, the same path as the button, because the button and the elevator floor are both accelerating with the elevator. So I can draw the same kind of shape, but I don't know how much that is. I don't know if it intersects here, here, here. I'm just sketching these graphs to try to get a visualization of what's going on. But it follows kind of the same path as the button, but just starts at the same position as Mary. So we know for sure that they start at the same place. And we also can kind of see that no matter where I draw this parabola, it is going to cross Mary's path again. Which makes sense physically, because we know that if a cat jumps in an elevator, it's going to fall to the ground again. It's going to land on the ground eventually. So, yeah, we know that physically. That's just a thing that happens. So what we have to do is find how much time she's going to be in the air. So what is the value of time when she lands again? So what we need to do is we need to think about her position, yc, as a function of time. And when does that equal the position, I'm going to call it ye, for the position of the elevator floor. So I'm trying to find where they're the same, because that tells me that she is on the floor at that point, either when we start, when she is jumping from the floor, or when they intersect again, when she's landing back on the floor. So all I need to do, I need to borrow my equation from up here for the position of the cat as a function of time. And then I need to set up the position of the elevator floor as a function of time. All right? So just like before, I'm going to start with my general position equation. And now, all right, before we had the button, which had an initial position, but we said that the floor is starting at the same place as Mary, so we called that 0. So my initial position of the elevator floor is going to be 0. The initial velocity of the elevator floor is also 0, but the acceleration of the elevator is still 2 meters per second squared. So I set that up. All right, and then again, that'll simplify down just like it did before. 2 over 2 leaves me with t squared. So now what I have to do is I have to come up here and set them equal. So this one's a little short, so I can rewrite this. V naught t plus, minus g over 2 t squared. That's my equation for the cat. And I'm setting that equal to the equation for the elevator button, which was just t squared. Not the elevator button, the elevator floor. Sorry. So again, I'm going to subtract my t squared over, and I'm going to have v naught t minus g over 2 t squared minus t squared equals 0. And again, I'm going to plug in my 9.8 just so I can combine these two terms. So it'll be 9.8 over 2, which is again 4.9. So with the extra minus 1, so v naught t minus 5.9 t squared equals 0. This time I can factor out t, v naught minus 5.9 t equals 0. Again, it makes sense that t equals 0 is one of our solutions because the elevator and the cat start off in the same place. So at time equals 0, they do have the same position. So now we just have to find the other solution because that's going to be our more helpful one. So if I add 5.9t to both sides, I get that v naught will equal 5.9t. I can divide by 5.9 on both sides. And remembering that our v naught, or Mary's initial velocity, is 4.85, I divide by my 5.9, and that equals my time. So if I punch that into a calculator, I'm going to get 0.82204. We'll just round it there. 04 seconds. All right. Units, very important. All right. So that's the time that Mary is in the air before she lands again on the elevator floor. Now we need to figure out the greatest distance above the elevator floor that she's going to reach. This is trickier because the greatest distance above the floor might not be where her velocity is 0. We can't just use the same method that we did before because we can't just set her velocity equal to 0 and say that's going to be her highest point, because clearly the elevator floor could be right, like that could be when she's landing. The elevator floor could be catching up to her at that point. So really what we're looking at is the difference between Mary and the elevator. And I want to say that position of the cat minus the position of the elevator floor, I want to find where that is at a maximum, right? That will be her highest point because that'll be her highest point above the elevator floor. So how do I figure out that? Well, we were talking about it a little bit with the previous problem, but if I look at Mary's position relative to the elevator, right, because remember that's what we did, right? If I'm saying that this is the position relative to the elevator, what we did when we set them equal, then I subtracted my position of the elevator over to the other side. Then what I ended up with was yc minus ye, which is exactly what I had up here. And I simplified it, and it simplified into a beautifully symmetric parabola, right? 0 is a solution of this parabola. Her distance above the elevator floor follows those rules that we said before, where her time to apex is half of the time it takes her to fall back to the ground or land back on the ground, right? So if I were to graph this, right, I have her position, I have the elevator's position. If I wanted to do her position above the elevator, right, it would happen a little bit earlier than her, right, landing her original apex. So maybe it'll look something a little bit more like this, or my apex is a little bit before then. All right, my time to land will be twice my time to apex. If I know my time to land is 0.822, I just divide it by 2, and I'll get my time to apex. That'll be my time to land, that'll be my time to apex, will be about 0.411 seconds. All right, I just cut it in half. So if I'm trying to find her maximum height above the elevator floor, I want to find yc minus ye, or the position of the cat relative to the elevator floor, at the time where it's at a maximum or the time where she's at the apex of that height, but not the apex of her original jump, the apex of this new kind of relative jump. So all we have to do is we can take this equation, because remember we said that it's just the pieces put together, right? My position of the cat is right here. My position of the elevator, right? Minus the position of the elevator. So instead of setting this equal to 0, I want to find out what this is at 0.411 seconds. So I'm going to borrow that equation there. And we're going to say that instead of equals 0, I'm going to start plugging my numbers. So I'm going to 4.85 for that initial velocity. My time is 0.411 seconds minus my 9.8 over 2 times my 0.411 squared minus 0.411 also squared. All right. And what that's going to work out to, when I do all of this, punch it into my calculator, it's going to give me a maximum distance of 0.9967 meters, right? Now, we want to make sure that does that make sense in the context of our problem? Well, if that's the greatest distance above the elevator floor that she reaches, it makes sense, at the very least, that it's less than the 1.1 meters that the button was at. That tells us, again, that she never reaches the button. Her maximum height doesn't reach the height of the button. So this 0.99 or 1 meter-ish, it's going to be around 1, maybe if you used 10 or rounded differently. That answer makes sense in the context of our problem. She's not going to be able to get as high because the floor is accelerating up under her and the floor is catching up to her as she's jumping. All right. So an infamous problem, but not so bad, I promise. Now, our final adventure with Mary and her kitten in this strange new world with a whole new gravity. We need to find out, how high can Mary jump on Twillow? Well, all this is asking us for is, how high can Mary jump? That's the height of her apex of her jump. So what is the value of her height at the time when velocity is 0? So that kind of thing, I can use my third kinematics equation. V naught squared equals 2a delta y. Or instead of using delta, we'll call it y final minus y initial. If I say that my initial position is 0, and I'm also going to say, because I'm trying to get to the apex of the jump, that her final velocity is 0, I still have her initial velocity solved from a couple of problems ago. But now, instead of her acceleration being g on Earth, it's going to be this new kind of g. So I can plug that in. 2 times g, it's still going to be minus g because it's still down and I'm still saying that up is positive. And I'm solving for her y final, her final position. Now I want to know how high can she jump. So I have a negative on this side and my negative on that side that I can just get rid of. And then if I am solving for y final in this case, before I was solving for v naught, now I'm solving for y final, I'm going to divide both sides by 2g. I guess I'm just dividing by negative 2g. So my y final, or the maximum height that she can jump on Twillow, is going to be v naught squared over 2g. And punching all of that into my calculator, I'm going to get 0.9967 meters. But that should look familiar, because that was exactly the maximum height that she could jump above the elevator. Now let's keep that in mind as we keep progressing through our problem. If Mary jumps on Twillow, how much time will she be in the air for? So I need to find out the time when she hits the ground or lands back on the ground. So Mary's position as a function of time being y naught plus v naught t plus 1/2 a t squared. I can set this up. I want to find when her final position, when she's landing back on the ground, means I'm setting this equal to 0. Her initial position, as we've said before, is still 0. So it'll be 0. Sorry, I probably should have said this g was my 11.8, whoops, 11.8 meters per second squared. That's what I plugged in for this. I just didn't say it because I just used g again. But my initial position is 0 again for this new one. I still know my initial velocity, and my acceleration is still going to be minus g. It's just, again, remember that that's our 11.8 meters per second squared. That's our new g for this new planet. So if I keep going and I solve for t, I can factor out t times v naught plus, I guess I can switch that to the minus g over 2 t squared. Nope, that's not squared anymore. And again, we can see that our t equals 0 is a solution, but that's not very interesting, so we're going to solve for our other one. G over 2t equals 0, and I can say v naught will equal g over 2t. I multiply both sides by 2 and divide both sides by g. Will give me that t equals 2v naught over g. And again, remembering that that g is that 11.8, so it'll be 2 times my initial velocity was that 4.85 meters per second, and my g in this case is 11.8 meters per second squared. And again, punching all of that into a calculator will give us 0.822 seconds, which also should be familiar from the time that it took the cat to land on the ground in the elevator, 0.822 seconds. Now, based on a comparison of the last two problems, which I've been hinting at a little bit, how does the experience of being in an accelerating box compare to the experience of being in different gravity? Well, we just saw it with the numbers, but I got the exact same values if she was in stronger gravity than if she was in an accelerating box. So the conclusion that I can draw is that they're the same, right? If the floor is accelerating upwards to meet the jumping cat as she's jumping, it's the same as essentially saying that it seems like she's accelerating towards the floor faster, right? So that's a stronger acceleration from gravity is what it seems like. And if I look at my equations too, I don't think I ever wrote them all the way out like this, but I have my position of the cat in our, on this weird planet was our 4.85 t minus, and it was the 11.8 over 2, because again, that was our new g. And solving for that, yc and simplifying that, I'll get my yc is 4.85 t minus 11.8 divided by 2. That was 5.9 t squared. And we might recognize this for my cat's position above the ground is the same exact equation as my cat's position above the elevator floor. I'm just trying to find it. It was over here. All right, so if I were to simplify this, it'd be 4.85 times t minus, well, it was my 9.8 divided by 2, so it was 4.9 minus the extra 1, so it'll be minus my 5.9 t squared. That's my yc of t minus yet. Right. So it's the same exact equation, which makes sense, right? We were getting the same values and all that. So it's the same exact thing. If my reference frame, if my elevator is accelerating, the only effect it has on my problem is it makes it seem like gravity is a little bit stronger, right? Which we feel. If you ever ride around in an elevator while I'm accelerating upwards, I feel like I'm kind of getting stuck to the floor. I feel heavier in that moment. And when I'm accelerating, when the elevator is accelerating downwards, I'll feel a little bit lighter, right? So it'll be like gravity is not quite as strong. So that's the fun part about this one, that we just solved the exact same problem twice. It's just that the cat in the elevator parts made it seem a lot more complicated than it was. All right, so moving right along, we still have two more to talk about. We have a hiker standing on top of a mountain that is at a slope of 45 degrees. They kick a rock horizontally off of the mountain at an initial speed v0, right? So when I'm given at an initial speed v0, that tells me that v0, I can treat v0 as one of my known values, right? So this is saying that if we were in some situation like this, if we were given an initial velocity, could we figure out where on the slope the rock lands? So given any initial velocity, we want to be able to figure out where on the slope the rock lands. So we treat v0, even though we don't have a number for it, we pretend that we do. Okay. Sails through the air until it lands on the lower slope. Now, we have to think very carefully about how we are describing the rock landing on the slope in terms of math, right? And a very helpful suggestion here is to draw a picture. So that's exactly what I'm going to do. I'm going to draw the slope, which is at my 45 degrees. And I'm going to set my coordinates. This one, just for funsies, I'm going to set my 0 up here. And I'm going to say that down is positive, just to shake things up, right? So down and right are going to be positive. Now, this will work with any coordinate system that you choose. I just like this one because it makes sense in my head when I work out this problem about what I'm actually talking about. But again, I can set my 0 wherever I wanted to. It just changes what I'm solving for and what my initial conditions are, or in terms of my initial position in the x and y. I also know that my velocity is horizontal. Right? I kick the rock off horizontally, which means that my v0 is going straight to the right. And that might give me a trajectory that looks something like that. I'm not very good at drawing parabolas today, apparently. Right? So it lands back on the slope at some point. Let's say that it lands here. So I want to think about, how do I know that the rock has landed back on the slope? Well, if I look carefully at my coordinates, because usually when we talk about something landing, we say that the y position is 0. Right? It's landing back on the ground, so it started wherever and it's landing at what I called my 0y. This case, I set my 0y up here, so we know we're definitely not at 0y when we land. But there's something else interesting about this, right? Because I drew my x and y kind of axes, and it gives me this right angle, so I have a 45, 45, 90 special right triangle. All right, we can check that because my interior angles will add to 180. So I have my 45, 45, 90 right triangle, which also means that this triangle is isosceles, right? This leg of the triangle is the same length as this leg of the triangle. And coincidentally, this leg of my triangle, well, that's just my y coordinate, or my final y position from 0. And this leg of the triangle would be my final x position from 0. So if the rock is on the slope, my x position has to equal my y position. And this will be true anywhere that I, say I didn't kick it as hard and it landed here. That's still a 45 degree angle. That's still a 90 degree angle. So my y still equals my x. Okay. So anywhere on the slope, y equals x. Now that's not necessarily true if it's off the slope over here, right? Because I'll have some x and some y. But that's our indication that we're back on the slope. That's what we're asking. So if I'm thinking about how I'm describing all of this and what I'm solving for, All right, I'm trying to solve for where on the slope the rock lands. So what is the value of, well, I don't know if we have a variable that says where on the slope the rock lands. So I'm going to make one, and I'm going to say that my distance from here to wherever I land, I'm going to call that d. All right. So my distance along the slope, or my hypotenuse of my 45, 45, 90 right triangle, the hypotenuse of that triangle, that's going to be how far down the slope the rock lands. So that's what I'm solving for. What is the value of d at the time when x of t equals y of t? Right? That's how I phrase that first one. Now we're going to actually do the algebra and sort it out, right? We're not going to get a number for this, right, because we were given an initial speed v0. So I'm going to keep everything in terms of all my variables. So I'm going to think about what do I know and what do I not know in this problem. Right? I have my x0, x of t. I have my v0 x. I have my ax. I have t. Ooh, I skipped v of x, vx of t. All right, but we don't really care what that is because we aren't solving for the speed with which it hits the ground, and we also don't know what it is, so we can kind of ignore it anyways. But it's good just to write it. Vy of t, same exact thing, ay and t. All right. So I know because of how I set my origin that my x0 and my y0 are both 0. Well, I don't know what my x of t and my y of t are. In fact, I need to solve for them if I'm going to find d, right? Because I need a leg of the triangle in order to find the hypotenuse. So eventually, I'm going to be solving for those. My v0 x and my v0 y, well, that was a step that I skipped that I probably shouldn't have. But normally, the first thing that I do when I'm given a vector, my initial velocity vector, is I break it into its components. But this vector doesn't have a y component. It's not going up and down at all. So my v0 y is 0, which means all of this initial velocity is going in the x direction. So my v0 x will be v0, which is, again, this is a known value, right? So I can just use that as my variable. I'm going to leave my answer in terms of that, and v0 y will be 0. My acceleration, the x, for an object in free fall, 0 meters per second squared. And my acceleration in the y, well, we've automatically defaulted to negative g a lot of the time. But remember, gravity is down, right? And this time, I decided to say that down is positive. So just to shake things up, our acceleration in the y direction is a positive g. All right. Now that I have all my stuff set out, I need to find the time when y of t equals x of t. So I'm going to set up both my equations. X of t will be x0 plus v0 xt plus 1/2 ax t squared. And again, we said x0 was 0, ax is 0, and v0 x is just v0. So that gives me that my x of t equals v0 t. And then for my y of t equation, y of t is y0 plus v0 y t plus 1/2 ay t squared. And again, I said y0 was 0. I also said that my v0 y was 0. And I knew my acceleration was positive g. So that gives me my equation of y of t equals g over 2t squared. So now I have to find the time when these two are the same. So I'm going to set them equal to each other, set my two equations equal. So I have v0 t equals g over 2t squared. Now, to solve this one, I'm going to subtract v naught t from both sides, so I get everything just on one side. So I'll get 0 equals g over 2t squared minus v naught t. And we have ourselves another quadratic, so I'm going to factor out t, which will leave me with g over 2t minus v naught. And again, we see that t equals 0 is one of our factors, which again makes sense because it starts on the slope. It starts when x equals y because they both equal 0. So that's not our interesting solution. Our interesting solution is going to be what we get from the other one. Okay. So if I add v naught to both sides, g over 2t equals v naught. I'm going to multiply both sides by 2 and divide both sides by g. So that's going to give me t equals 2v naught over g. Wonderful! I've solved part of the problem. Right? But even though I have a beautiful and maybe complicated solution, I have to remember that we still have to go back and solve for not only position, but we have to use that and then solve back all the way back for the hypotenuse of this triangle. So now that I have my time, I know the time when it lands back on the slope. I can take that and plug back into one of my equations. It doesn't matter which one, right? Because we said we set y of t equal to x of t. So they're both going to give me the same answer. So I'm going to plug it into my x of t equation. So x of t will equal v naught times t, which was 2v naught over g. And that's going to simplify. X of t will equal 2 v naught squared over g, right? Because my v naughts multiply together. And just to check it while we're here, I'm going to also solve for y of t by plugging in my time. I don't have to do this because they should be the same, but we're just going to do it to check our work. So I'm plugging my time as 2v naught over g, and I'm squaring that. So my squared, because it's all multiplication and division inside this, inside the exponent, I can distribute my squared down through everything inside that exponent. So it's g over 2 on the outside. And then 2 squared is 4, v naught squared over g squared. Right? And since it's all multiplication and division now, I don't actually need these parentheses. I was just redrawing them so that we saw where one fraction ended and the other began. But now I have a g in the numerator, which will cancel with one of the g from the g squared in the denominator. I have 4, which when divided by 2 will give 2. And my v naught will stay. So that gives me my simplified expression that y of t equals 2 v naught squared over g, which is exactly what we got for my x of t equation with just a little less work, right? But now, again, that's not what I was trying to solve for to answer the question. I want to get this hypotenuse. So if I set up my Pythagorean theorem, I know x squared plus y squared equals d squared. So if I'm solving for d, I just have to take the square root of both sides. So d will be the square root of x squared plus y squared. And I can plug in the expression that I found for x and for y. So it'll be 2 v naught squared over g squared plus 2 v naught squared over g squared, and I square root it. All right, now this is just a thing plus itself, so it's really just 2 times that thing. We get square root of 2 times 2 v naught squared over g. That's all squared. And again, since I have this only multiplication under my radical now, under this square root, really what a square root is raising something to the 1/2 power. So I can, same way that I had when I had only multiplication over here, I can distribute my exponent into the multiplication and division. I can do the same thing with my square root. So that's going to be square root of 2 times square root of 2 v naught squared over g squared. Now, this square root, all that does, it just serves to get rid of that squared. So that means all of that just cancels itself out. And d equals the square root of 2 times 2 v naught squared over g. Right? And now if I go back to the beginning of my problem, my answer that I've circled, that is the distance down the slope that the ball will land given an initial velocity. My answer is in terms of only things that I know. There's no x's or y's or any thetas or anything like that left in here. I know g, right? It's my acceleration from gravity. And I'm given that I know v naught, even though I don't have a number for it. Right? So that means that this is a valid answer. And I always want to do that check at the end to make sure that my answer is, first of all, it's not in terms of itself. So it's not like there's not a d on both sides of the equation. And also I want to make sure that it's in terms of things that I'm allowed to leave it in terms of, things that I know in this problem. All right, on to our last problem. We've almost made it. So we have an airplane flying at a speed of 200 kilometers an hour relative to the air around it. There is a wind blowing from north to south at 40 kilometers per hour. Right? So this is the old version of the problem. So the new version, I'm just realizing, the new version had wind blowing from west to east, and we pointed the plane north to start. So if the pilot points the plane north, we want to draw the vectors describing the problem, and we want to get the speed of the plane relative to the ground. So I want to think about how to do this. I never want to start with a very complicated situation, so I'll start piece by piece. So the first thing that I know is that the plane is pointing north. And that is, if there was no wind at all, that is the direction that the plane would be flying. So that's the direction that the engines on the plane, I'm an aerospace engineer, right? So that's the direction the engines of the plane are pushing it. And that's going to be our 200 kilometers per hour, right? I'm going to call it VP, though, for velocity of the plane, right? So without wind, that is what the plane would be doing. But there is wind, and that wind is pushing us to the east. So that's how I get my velocity of the plane, and my velocity of the wind is pushing us to the east. So the result of this, what I do is I add my vectors, and you notice that I drew them tip to tail, because when I add vectors, I draw my first vector, and then I start where I just left off and draw the second vector, and my resultant starts where I started and ends where I ended. So if this is the velocity of the plane, this is the velocity of the wind pushing us to the side, which was our 40 kilometers per hour. Sorry, I forgot the number there. Then this result, that will be my velocity of the plane relative to the ground. So really what we're saying, this is the velocity of the plane relative to the air. This is the velocity of the air relative to the ground. And together, they combine to make the velocity of the plane relative to the ground. And because I was given that we're pointing the plane due north and the wind is pushing us due east, I put that 90-degree angle there. And we can solve this. We can get our speed relative to the ground, which is the magnitude of this velocity. We can get our speed using our Pythagorean theorem. So it just says that this squared plus this squared equals this squared. So my velocity of the plane relative to the ground can be square root of like 200 kilometers per hour squared plus my 40 kilometers per hour squared. Now, you may have also noticed that I didn't convert my units. Usually the first thing that I do when I see something that's not in meters, seconds, kilograms, those kinds of things, are base units. Anything that's not in base units, usually I don't even write it down as kilometers per hour. I would convert it directly into meters per second. But because we're just dealing in velocities in this case, right, it's not going to change anything. I'm just adding a velocity to another velocity. I'm not adding their numbers, but I'm adding their vectors. So as long as both of my input velocities are in kilometers per hour, my result will just be in kilometers per hour, and I can keep it like that. All right. So speaking of that result, once I punch this into a calculator, I'm going to get that it's going at 203.961 kilometers per hour. Right. So that's the speed of the plane relative to the ground if it's flying north and being pushed east. Sorry, I'm bad at... I looked at the wind and I said west because it's W, but we're being pushed east. So I want to think, does this answer make sense? Well, my 200 kilometers per hour is getting me north, and then I have some additional velocity because the wind is also pushing me. So a larger velocity than what I started with would make sense because I'm not fighting against the wind at all, which will then be the case in our second situation. Right? If the pilot wants to fly due north of the airplane's current location, I have to draw the vectors describing the situation. Then I need to compute the angle the pilot must orient the plane and the speed of the plane relative to the ground in this situation. So what I did before is I set up my velocity of the plane plus my velocity of the wind equals my velocity relative to the ground. Right? So tip to tail like that. Well, now I don't know the direction of the velocity of the plane just yet. But what I can do is I can draw what I want the result to be. Right? I know that the velocity of the plane relative to the ground, I want that going due north. And I know that wherever I point my plane in whatever direction, that the wind will be pointing due east. Right? The reason I drew it down here, when I'm adding vectors together, I do tip to tail. But in this case, I want to do the same exact thing, but I don't know one of my vectors. So I can say v wind vector plus my v plane vector equals my velocity of the plane relative to the ground vector. Right? So what I have to do is, if I'm starting with v wind, before I started with v plane, it doesn't matter what order I add them in, but if I'm starting with v wind, I know that my resultant vector will start in the same place that the first vector I'm adding does. Because I add my first vector and I add my second, and my resultant starts where the first one started and ends where the second one ends. And I know that the second vector starts where the first one ended and ends where the resultant ends. So that tells me that when I'm connecting my vectors together, what vector can I add to my velocity of the wind to end up back over here? Well, the vector that I can add is this one. Right? Velocity of the plane. And again, since my plane is trying to go due north and my wind is due east, I have that right angle there, which helps a little bit with my solving this one. So now all I have to do, I have my triangle set up because again, my v wind vector plus my v plane vector, right, which I can do in either order. But since I set them up in this order, I go tip to tail and I draw my resultant vector from the beginning to the end. So had I had all my vectors, I could have drawn them in order and said this one plus this one equals this one. But I kind of had to work backwards just a little bit because I didn't know the direction that my velocity of the plane was going to be going just yet. So now, given that I have my triangle all set up, I just need to find the direction that the pilot is facing, so the direction that I'm trying to fly before the wind causes problems. And I need the velocity of the plane relative to the ground. So I'm going to choose to solve for this angle theta because it's the same as this angle theta, and I can. That's the one I decide. That's what I decide to go for, because that tells me the direction of my plane's velocity relative to one of my cardinal directions, right? So if I were to be solving for that angle, maybe I don't know which trig function to use. I'm just going to remind myself of these magnitudes real quick. Right? Maybe I don't know which trig function to use. I'm not going to waste any brain power trying to figure it out. There's only 3 of them, right? So if this is my theta, I'm just going to throw a trig function at my triangle and see what happens. So I have my SOHCAHTOA. So I'm just going to start with sine because it's the first one. So my sine of theta is opposite over hypotenuse. That'll be 40 over 200. And in this case, because I know 2 of the legs of my triangle, and I can get the third, we're going to get that using Pythagorean theorem in a minute. It didn't really matter which of my trig functions I ended up using. I always recommend we want to base our calculations off of numbers that were given in the problem, right? We were given our 200 kilometers and our 40 kilometers per hour. So if I were to calculate my second leg of this right triangle, and maybe I punched something into my calculator wrong and I got a weird looking number, and then I used that to solve for theta. Maybe I did cosine, which would be adjacent over hypotenuse. If I used that to solve for theta, then both my velocity vector and my theta value would have been wrong. Like my process would have been correct for finding theta, but the number would have been wrong. So when in doubt, or just as a precaution, I like to try to base all my calculations as much as I can off of numbers that were given in the problem, just so I don't have like that cascading error effect. But either way, I'm going to take the inverse sine of both sides. So sine inverse of 40 over 200 will give me theta. And punching that into a calculator tells me that theta is going to be about 11.537 degrees. Right? And whenever I'm doing sine or inverse sine, I want to make sure my calculator is in degrees mode, or if we're doing something with radians, probably not just yet, but if we ever do anything with radians, it's in radians mode. Just always check the mode of your calculator. It's an easy way to not make a mistake. But I'm not quite done because this doesn't fully define the direction. Because if I just say, oh, it's going 11.5 degrees, I don't know with reference to what, right? So my 11.53 degrees is this angle here, because we said it was the same as that angle there. And that's the direction of my vector relative to north, right? So it's relative to the north, but it could be east or west of north, right? If it was going this way, I would be going east of north, and this way is now west of north, right? So that's telling me this is west of north. So that's kind of how I decipher this. I start by pointing my pencil in the direction of north, and I swing towards the vector, right? I'm sweeping out over that angle, and I'm sweeping in the westerly direction of north. So that's the difference between my west of north and north of west. It's an important distinction because it's the difference between here and like down here, right? Because that's my 11 degrees. So it's kind of a big deal. We want to make sure we're communicating things clearly. So now I need to get the speed relative to the ground, which I can do with Pythagorean theorem. So I'm going to set that up. Velocity of the plane relative to the ground plus squared plus the velocity of the wind squared equals the velocity of the plane squared. And I have to set it up a little differently from before right? Because before I knew my two legs and I was solving for a hypotenuse, but now I know the hypotenuse and one of the legs, and I'm solving for the other leg. So my velocity, that's a P, velocity of the plane relative to the ground will be, so I can subtract this over to the other side and then square root. So it'll be the square root of VP squared minus VW squared. And then I can plug in my numbers for that. So it'll be 200 squared minus my 40 kilometers per hour squared. And punching all of that in to a calculator will give me 195.96 kilometers per hour. And I want to think to myself again, does this make sense? Does it make sense that it's less than the 200 that I started with? And this time, it does make sense that it's less than the 200 I started with, because now not only am I trying to fly north, but I'm trying to counteract the wind. So I'm countering the wind while also giving us that northern, the northern heading, our northern direction. All right. And it also makes sense that we end up flying west of north, because if the wind is trying to blow me east, I have to fly west in order to cancel that out. So I use some of my velocity to cancel out the effect of the wind, and the rest of it can just be taking me towards the airport that is north in that northern heading. All right. Well, that's all I got for you guys. So I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this or anything else that you want me to try to explain. And I will do my best to try to explain it, because I guess Sydney explains stuff.